Alright, DBF team, welcome back to another one of these online lecture series. Hopefully it's been going good so far. Up to this point we've been talking about forces and we've been talking about moments. We've gone ahead and derived essentially 6 equations for three-dimensional case and 3 equations for the two-dimensional case. We've talked a lot about point force applications and how that transitions into reaction forces and moments at the support. Today, we're going to be looking at something a little different but along the same lines. Remember that everything that we're doing here is we're working to simplify a real-world example and put it into something that we can calculate and interpret a little bit easier. Now, today we're going to be talking a lot about distributed forces, and after this lecture I can really start to tie in a lot of these concepts into what we've been doing with the plane this year. Think about today and the past videos as laying that foundation for you guys. By understanding the concepts here, you're going to be able to understand more about what happens with the plane, what happens with the wing loading during flight, what happens with the center of gravity calculations we made for the body, and all of that good stuff. So hang in there, we're almost through sort of the fundamentals. But today, we're going to be talking about a distributed load. Now, if I go ahead and I draw, again, my favorite example, the cantilever beam, let's go ahead and do that. Now, I want to mention something real fast here. This cantilever beam, it's not my favorite example for no reason. In fact, if you're going to simulate any sort of wing loading on the plane, you can typically assume that the wing is essentially a cantilever beam because it's fixed by the fuselage. Imagine this side to be the fuselage, and it's free at the wingtip, right? This is a very simple representation of how the actual wing is mounted onto the body of the plane. So if I need to know the reaction forces at the joints when I mount this sort of wing to the side of the plane, on top of the plane, however I do, then this gives me a good foundation for calculating that. So one of the things I got to mention here is up to this point we've been doing a lot of point force application, and what that looks like is I pick a spot on this beam and I apply a force. For example, I could do it here. There we go. I've applied a force F at that point. It's a point force application. And we've already learned that I can go ahead and calculate the reaction forces under a point force load. I simply sum all of the forces in the x and y direction, and then I go ahead and calculate all of the moments. For example, this force is acting at a set distance from the support, therefore there is a reaction moment about the support that must resist this, otherwise we'd be pivoting. So we've talked about all of that. However, in real life, we don't typically work with point force loads. We work with a lot of what are called distributed loads. So a great example that my CEE professor actually gave to me was, think about a roof, right? So think about a roof that's covered in snow. Snow has mass, but that mass, that force, the mass times gravity, which is a force, is not being applied at one point. Instead, if I were to draw sort of a distributed snow force, imagine there's a bunch of snow on this beam, it might look something like this. Right? Where essentially this force is acting at every single point on the beam. It's a distributed force. It's like a weight force, a snow force. I don't know why I called it a snow force, but in this case it is. It's the force due to the weight of the snow distributed across the beam for where it's sitting. So this here is, I'm going to classify it as a rectangular distributed load. Now, why rectangular? I mean, I don't even know if this is terminology that's used in the classroom, but for me, I look at this, I see a rectangle. Right? And there's a very specific reason why I'm going to classify this as a rectangular load, and you're going to find out real fast. But this distributed load here, this distributed force that's acting on my beam, in order to simplify this, because imagine I want to calculate the moment, and I have to take every single one of these distributed points times a distance, d1, d2, d3. it would be a nightmare, right? And then imagine I had to sum up every single one of those arrows. There's an infinite number of those arrows, right? Because it's a distributed force across every single point on the body. It would be quite difficult. However, instead of doing that, what I can do is I can sum up the summation of all of those forces and place them acting at a certain point on the body. Okay? Now, what we're going to do essentially, in order to do that, is we have to calculate something called the centroid, or the center of load, in this case, since it's a loading force, of this distribution. And that's what we're going to talk about today, is how to calculate the center of load, center of mass, etc., etc. So in this case here, let's say that my distribution is represented by this. Let's say one of these magnitudes, if I were to make a magnitude here, that's going to be equal to 10 newtons. And let's say that my beam has a length of 10 meters. Okay. Now, if I want to go ahead and solve for the force, right, the summation of the force by this distributed load acting on the body, what I'm simply doing is I'm solving for the area under the curve of the distributed load and setting that equal to the total force, right? You guys have all done integration, right? If I want to go ahead and figure out what the summation of all of this load is, I'm going to integrate everything under that boundary condition, or under that upper bound, right? As I move from left to right here, I'm going to continuously sum every single segment until I come up with what the final distributed load is on the beam. So in this case, you can probably guess already, but it's quite simple. If I have a magnitude of 10 newtons times, and again, let's define our axis. I always forget to do this. That's the x-axis. 10 times x. As I move this way, right, the rectangle, the equation for the rectangle, again, rectangular load, is going to be, as I'm moving in this direction, I have a height of 10, and my base is equal to x, right? So 10 times x, and when x is equal to 10, then I have my total load across the entire beam. So 10 times x is going to equal my load. So let's just call that F as a function of x. And at the very end, when x equals to 10, my load is 100 newtons. All right? So that is the total sum of the distributed load on my body. Quite simple. However, where do I place this load? Where is this load acting? Because remember, we have to calculate moment. And the moment, due to this distributed load, has to be essentially accurate, right? We can't just say, okay, we got 100 newtons and it acts like right here. Because then what? The moment created by that would be 0. But if I look at this element out here is creating a moment. So therefore, by default, it can't possibly be 0. So we have to figure out an area where we put this so that the moment is still valid. Because remember, we're making this simplification to take this distributed load, turn it into a point force at a specific location in which the moment is still properly represented. So the way we do that is we calculate what's called the center of load, the centroid, however you want to say. It's basically the equivalent location at which this distributed load can be applied as a point force without changing the characteristic of the load. Now, basically, when you're thinking about what a centroid is, if you're thinking about what a center of mass is, you're basically thinking about where is the one point on this distribution where I have an equal amount of stuff to the left and an equal amount of stuff to the right. For a rectangular load, this is quite simple. If I want to balance this load at one point, any one point, well, that one point's got to be where I have an equal amount of stuff to the left and right. So in that case, if I simply cut this rectangle in half at 5 meters, would you agree that I would have 50 newtons on the left and 50 newtons on the right? What that does is I'm saying, okay, that's where the load would balance. That's where the center of load, center of mass, however you want to call this, the centroid, is. So I can go ahead and take this summation of the load and apply it at the center of load right here. And this will vastly simplify my solution when I go to solve. Because now, instead of dealing with a distributed load that's acting at every point, I'm simplifying it down to a point force, which we already know how to deal with, at a specific location, and the location is the centroid or center of load of that distributed force. Now, there's a bunch of online tables, where for different, basically, shapes, they show you how to calculate where the centroid is. And I highly recommend, I think I'll try to throw one of those up on the screen real quick so you guys see what that looks like. But I highly recommend you guys really get familiar with that table. Because some of the locations of the centroids for different bodies aren't quite so intuitive. Let's put it that way. So yeah, let's go ahead and do one more example before we leave today. Now remember, first and foremost, we want to draw our boundary conditions, our reaction forces, right? We know that a cantilever beam can resist 3. We're going to go ahead and draw those. Okay, and then little coordinate system. Always do this when you start a problem. I'm not the best at this. I'm going to try to be better for you guys. But this is really important. You have to define your reaction forces and your coordinate system, or the rest of this is just really difficult. Alright, now we're going to do a different type of distributed load. Instead of doing something easy like a rectangular load, which is very intuitive, the centroid is of course going to be at the center of the rectangle. We're going to do something a little different. Okay, here we go. So we have a cantilever beam under distributed load in a triangular pattern. Now, the first thing I need to do here is I need to simplify this load to a point force at a centroidal distance on that load, right? One more thing, let's go ahead and define how long the beam is. Okay. So let's say the beam is 9 meters long. This is very intentional because, as you guys are going to see, I like to make things a little easier for myself. So here we go. We have a triangular load. The max is at the wall at 20 newtons, and it decays to 0 at the tip at 9 meters. And I want to go ahead and figure out what the point force load is. And that's quite simple. You guys all know the equation for a triangle, 1/2 base times height. So if we apply that real fast, we go ahead and we get, I'll do it up here. Okay, if we go ahead and apply that, we go ahead and get a load of 90 newtons equivalent. Okay, now where does that act? And again, we go back to our tables. I just so happen to remember, and again, this table I'm going to have up on the screen for you guys while I'm talking about this. In the table, you can go ahead and figure out where the centroidal location of a triangular distributed load is. But for me, I happen to remember it. So I'm going to take that point force and I'm going to apply it at a distance of 3 meters. Because I know that the centroidal distance on a triangle is 1/3 the total length of the triangle. And it's of course going to be on the side closer to the max. Because if I were to balance this, what I'm saying is, if I take this triangle and I balance it at 1/3 the length, and this over here would of course be 2/3, that this triangle will balance. It won't rotate. That's where the centroid is. I'm saying the centroid in the x direction is along this line. And do note that there's also a y direction for a centroid as well. In the case of the triangle, that will be somewhere around here. But yeah, so keep in mind, that's what a centroid means. It's where I can balance the load. So now that I've made this simplification, solving the rest of the problem is quite easy. Because I have a point force load of 90 newtons at 3 meters away from the wall. Which means my moment due to this is of course going to be 90 times 3, 270 Newton times meters, 270 Newton meters. that's going to be acting, and again, look at the way that the load is applied. It's going to rotate clockwise. Therefore, my resisted moment must be counterclockwise. So I know what M is. M is going to be equal, and I've already drawn it counterclockwise, to 270 Newton meters. And of course, we have no force in the X, so the reaction force in X is going to be equal to 0, and the reaction force in Y is of course equal to the sum of the distributed load, which is 90 newtons, in the positive Y direction. So really, as you can see here, it's not much more of a complication to go ahead and add a distributed load into the problem, because we can always simplify this down to a point force load, which we're very comfortable dealing with. So hopefully this makes some sense. This concept is going to be very important when we look at wing loading, because if you think about it, wing loading is simply a distributed lifting force across the entirety of the wing. So that sort of distribution is going to become very important in later videos. Also, this concept of a centroid, if you guys knew, as you guys know, I was in charge of calculating the center of mass for the airplane, the CG, the center of gravity location of our entire airplane. And all of these techniques, the centroidal calculation, I applied to the center of mass calculation for the airplane. And next video, I'm going to show you guys exactly how I did that. So again, thanks for watching. Hopefully that made some sense, and I'll see you next video.